Lecture 12. We have already seen counters, some types of counters, the synchronous and the asynchronous, and I'm going to do another counter. Before that, remember when we did the gates, we first showed you the gates, and then we said, okay, now we can put the gates together to do like a multiplexer, like an adder and all of that. And then the same thing with these flip-flops. We can put them together to do some designs, some functional units. And the very first functional unit I've shown you with these flip-flops are the counters. So I'm going to talk a little bit about registers, and which is really not much, and then shift registers, and then I will talk about a different kind of counter, and then this section will end. Then we will go into controllers, okay, that we build out of flip-flops. Usually when we talk about registers, the situation is this: we have a flip-flop here, another flip-flop here, another flip-flop here, and when we wire the clocks of the registers of the flip-flops together, and the resets and all the control lines, right? Yesterday we talked about the reset set and all of those control lines. We call those flip-flop control lines, and usually, like I said yesterday, we don't get those involved in our design procedure, and we will see the design procedure, but those usually don't come into play and don't come into the procedure of our design. And then we have a reset and a clock, and if you have a situation like this is a 3-bit register. The outputs are shown there. Usually I use a different color for the clock and reset, indicating that clock and reset are things that you don't touch, you don't play with, and they don't come into your design procedure. And so these are the what we can call the register. Let's say I'm calling this A register. So this is A register, bit number 2, bit number 1, bit number 0. All right, and then these become the inputs of the register. Normally these are called the parallel inputs of the register. Okay, all right, in addition to the register that takes, like in this particular case, if we have a 3-bit clocks into the register, and then you read the output, and or it saves the output. In addition to this kind of register, we can have what is referred to as a shift register. I'm going to explain that to you now. Let's say instead of let's do a 4-bit now. Okay, let's put 4 flip-flops, and all of these are flip-flops. Okay, I'm not talking about latches. Actually, if you have if you do the design I'm doing right now with the latch, it's not gonna work. So this is again the clock, this is the reset. Okay, and each of these flip-flops has a D input, a Q output. Notice the reset is asynchronous. Okay. Now in the previous example, what I did was I just brought in parallel inputs and then put into the registers. And here, what I do, I take the output of one, feed it into the input of the other. And then the leftmost bit, I provide a separate input just by itself. All right. And let's call this one my SI, or serial input, and this is my shift register, and I'm going to tell you why I call this shift register. Bit number 3, shift register output bit number 2, shift register output bit number 1, and shift register output bit number 0. Let's say that at the very beginning I put in some data into my register, and let's say my register, meaning these outputs, are starting with value 0, 1, 1, 0. Okay. And also let's say that initially on my serial input I have a 0 sitting. Okay. This is sitting just like that without me clocking it or anything. As soon as I clock the circuit, each flip-flop it's going to take the so as soon as I clock it, each flip-flop, so the very first clock, each flip-flop it's gonna take its input, put it on the output. Okay. But then this is gonna happen simultaneously. At the same time that let's say for example this flip-flop is taking its input, putting it on the output, meaning putting the 0 on its 1 output, the flip-flop to its right, it's taking its input and putting it to the output. What it means is this 0 that is sitting here will go into this. Okay. But this is not the 0 that will go into the output of SR1. Actually, SR1, since it is taking the input simultaneous with SR2 taking the input, the 1 is the one that goes into the output of that. Okay? So that you don't get confused when you are doing this, usually best is to start from the right-hand side. Okay? Start from the right hand side. The rightmost, and this is a rising edge, the rightmost flip-flop is going to take a 1, which is sitting at its input. Okay, and this is this one. The flip-flop to the right is going to take, to the left, is going to take this one and put it here. What happens to the 0? Well, gone. Completely overwritten. Then SR2 is taking 0 and putting it into this. How about SR3? SR3 is taking the input 0 and putting it into this. That's with the first clock. I'm going to give my circuit another clock. Okay, and this time I keep my serial input value 0. let's again start from the right hand side. Starting from the right hand side, the SR1 is gonna take, see what is on its input is that 1 there, and therefore that 1 will be shifted to the right one place. Okay, shifted to the right one place. The SR1 has a 0 on its input, and therefore it will take the 0, put it on the output. SR2 also has a 0 on its input, and therefore this is what happens. SR3 has a 0, a blue 0, and therefore this is what happens with SR3. I'm going to give it one more clock and then look at what's happening. I'm going to put a 1 here, and then I'm going to clock it again. SR0 is going to take the 0. SR1 is going to take, actually, this is this. Okay. SR1 is going to take the blue 0. SR2 is going to take the blue 0, which is this. And then SR3 is going to take that green 1, which is this. What happens is you start with this, then you go to this, then you go to this, then you go to this. So you start with 0, 1, 1, 0, then becomes 0, 0, 1, 0. So what is really happening, 1, 1, I'm sorry. What is really happening, the contents of your register with each clock is shifting one place to the right. The contents of your clock, of your register with each clock is shifting one place to the right. And therefore I call this one a right shift register, or a shift register shifting to the right. Now this register has no way of doing a parallel loading into it. Okay? So if I decide that at one point I like to put some data in it, some parallel data into it, I won't be able to do it. Okay? This is what I'm going to do to resolve this issue now. I'm going to take some multiplexers . Okay, parallel input bit number 0, parallel input bit number 1, parallel input bit number 2, parallel input bit number 3. In addition, I will provide a control signal called a load signal. Okay. Now see how it works. If my load input is 1, then the circuit works just like a register. Right? If load is 1, the circuit works just like a register, like the 3-bit register I was showing over here. But then if load is so if load is 1, that's how it's going to work. And if load is 0, my circuit is going to work like a shift register. Okay, if load is 1, what happens is If load is 1, what happens is these parallel inputs on the clock will go to the output. This goes there, this goes there. That's if load is 1. And if load is 0, then you are working like a shift register, meaning that this one is taking this one is taking this one is taking this, and then the leftmost is taking the serial input. And this becomes your rightmost bit, which is also regarded as serial output. So that's a shift register, and this is how you use the flip-flops for building shift registers. Now, if you use latches instead of flip-flops, what would happen is, what would happen? If you use latches, what would happen? And let's say you put it in the shift mode, in the orange mode. It would be transparent. What happens is, as soon as you make the clock 1, the serial input all the way to the left passes through the entire register, makes everything that same value. Okay, so it's not going to work like a shift register. Exactly. All right. So we talked about register, shift register. Now you can make this shift register a little bit even more complex, right? You can make it a shift register to do parallel load, shift right, shift left, and what else? Parallel load, shift right, shift left, and do nothing. Let me do this for you. This is, by the way, called a universal shift register. I can build each one of my bits like this. A clock input, and then C1, 1D. I still have an asynchronous reset, and then I have 2 mode lines, M1, M0. Uh-oh. Hi. Are there people waiting to get in, or?
No, they're just two people talking.
Oh, okay, good. All right, each one of the bits, let's say bit number I of my shift register, works like this. It has a multiplexer. A 4-to-1 multiplexer. M1 is the most significant select input. M0 is the least significant select input. Okay? If M1, M0, if M1, M0 if it is 0, 0, it's called do nothing, which means that my shift register just takes the output from its own and put it back into its input. If my input is 0, 1, I am doing right shifting. Right shifting means that the flip-flop I is taking the output from flip-flop I minus 1. Then I have 1 0 is the left shifting. Left shifting means that I'm sorry, this was I plus 1, right? Right shifting means I plus 1 goes in there. Left shifting means that there is the output of flip-flop number I minus 1, okay, which now goes into my I input, and therefore I am performing left shifting, coming from the right going to the left. And this is done as such. And then my flip-flop can also have 1 1, which is parallel load, in which case I'm taking parallel input bit number I, putting it into the flip-flop. Okay, so you repeat this flip-flop 4 times, and that would be a shift register that can do right shifting, left shifting, and so on. The rightmost, the leftmost, and the rightmost. The leftmost flip-flop has a serial input that comes in from the left, okay, and that will be used when I'm doing the right shifting. So I have serial in coming from the left used in right shifting. Okay, my very leftmost flip-flop has an output which we can regard that as serial out coming from the left. Okay, actually serial out coming from the left is gotta be blue. Serial out coming from the left. And then when I'm left shifting, okay, when I'm left shifting, I have an input coming here, which is I am left shifting, so this is this, an input coming up from here, which is serial in from the right, that goes into flip-flop number 0. And then there is also the when you are right shifting, you also have serial out from the right that comes here. Okay, so let me clean this up a little. So this is actually coming from the output of I minus 1. Okay, and then bit number 0 has a has an output which is the same output, which is serial out from the right, Okay. Just 1 second. Let me do the coloring properly. When I'm right shifting, bit number 0 will be regarded as the serial out. So this is serial out from the right, used in the right shifting. In the left shifting, I have serial in coming in from the right. Okay, that go into the input of the rightmost flip-flop. All right, so this is a shift register, and all of these, they have a clock signal that ties all of them together. They have a reset signal that ties them all together. So we have done various kinds of shift registers, right shifter, left shifter, and then the one that shift right, shift left, and does everything else. I'm gonna go back to counters now, and we have done counters that count binary, but see, we don't necessarily count binary all the time. Okay, even this is a counter, something that counts from 000 to 010 to 011 to 100 to 111, and then back to 000. This is a modulo 1, 2, 3, 4, 5. 5 counter. Okay? I didn't say modulo 5 binary counter. If I had said modulo 5 binary counter, it would probably mean start from 0, then 1, 2, 3, 4, and then back to 0. It is a counter, but it's not counting any specific code. Okay? And I like to be able to design something like this. If the counter only goes in one direction, this is a modulo 5 up counter. If a counter goes in two directions, then it can be a modulo 5 up-down counter. That means it has a an input called up-down or up. If it's 0, it counts up. If it's 1, it counts down. Okay? And these counters, unfortunately, we cannot trace the inputs like what we did yesterday, which is going through the pattern, finding two ones, adding them together, and using them for the next bit. Okay, that's because it's not binary. If it is a gray code counter, we can do XORs and then do something similar to what we did yesterday also. But if it is a code that is not any known or any pattern, if you cannot find any pattern in the code, then you have to start with discrete logic and go through the procedure I'm showing you now to design this counter. To make things easy, I'm not going to do a modulo 5 counter yet. Yeah, let's do that. Let's do a modulo 5 counter, just like what I've shown up there. Okay? I'm going to first come up with my transition table. Okay? My Q2, Q1, Q0, 0, 0, 0, 0, 0, 1, 0, 1, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. Okay? If it's 0, 0, 0, Q2 plus, Q1 plus, Q0 plus become 0, 1, 0. Okay? Meaning this arrow. If it is 0, 1, 0, Okay, the next state is 0, 1, 1. So that's this one. If it is 0, 1, 1, okay, the next state is 1, 0, 0. 0, 1, 1, the next state is 1, 0, 0. So I did this. And if it is 1, 0, 0, the next state is 1, 1, 1. 1, 0, 0 is 1, 1, 1. And finally, if it is 1, 1, 1, the next state is 0, 0, 0. Okay? So, 0 becomes 0, 1, 0. 0, which is this one. 0, 1, 0 becomes 0, 1, 1. 0, 1, 1 becomes 1, 0, 0. 1, 0, 0 becomes 1, 1, 1, and so on. What happens to the rest of it? Well, the rest of it, I don't really care. The rest of it shouldn't even happen. I want to build this counter. When I get to this point where I have a transition table, see, the table I am showing you is a transition table. It's not the truth table. Okay? See, truth tables, they don't have timing. They don't have pluses. This is a transition table. It's showing the existing queues and then the next queues. This is Q2, Q1, Q0. Present queue and the next queue. Okay, how do I go from a transition table to a circuit? Well, before I showed you, I looked at the transition table and I found some patterns in it. I said, well, look, if the two rightmost bits are 1, 1, then I am toggling my input. But see, I'm not finding any pattern here. Maybe if I look, I will find something. But the right way of doing it is to go through generation of Boolean expressions for each input of the flip-flop. All right, now I'm looking at this. Eventually, what I end up with is something like this. I have 3 flip-flops which are providing my counter. They have reset. They have clock, which I don't really care about as far as my design is concerned. These are going to be there anyway. And then this becomes my Q2. This becomes my Q1. This becomes my Q0. When I get to the transition table, I have to decide what kind of flip-flops I want to use. Yesterday, because the transition table had that nice pattern to it, I said I'm going to be using the toggle flip-flop. Here, I don't have that nice pattern. Okay, so I don't have to use, or I don't have a pattern that matches the toggle flip-flop as well. Instead, what I have is a transition table that the present value is deciding the next value. Okay? So what I do is this. I say, I know a flip-flop called the D flip-flop that Q plus equal to D. Okay? What it means is this. The flip-flops that I'm after, they have D inputs, D2, D1, D0, that whatever I put on the D2, D1, D0 on this clock, and I clock the circuit, those become my next states. What it means is the following. Based on the Q2, Q1, Q0, the inputs for my D2, D1, D0, these three flip-flops I'm showing on the right-hand side, these inputs, and according to this characteristic equation, they become 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 1, 1, and 0, 0, 0. This table here is the transition table. It's showing the transition from, actually including this is showing the transition. Based on the transition, I have decided that I want to use D flip-flops, and based on the transitions, I have decided what is going to be on my D inputs. That second table, I'm calling it an excitation table. So the table that takes this output, that's my excitation table. That means these are the inputs provided for the D inputs of the flip-flops, so that these values will become the next value of the output of the flip-flop. Okay? So I start with my excitation table. The good thing about excitation table and transition table is that the transition table has that pluses there, which I'm still not used to it, right? Because what I'm used to is truth table, is Carnot map. There is no easy way for me to think of a transition table that has pluses and turn those into Carnot maps. Okay? Transition table is describing this. Okay? Next, on the other hand, excitation tables are describing this. Okay? What it means is going from transition table to the excitation table. I came from the output of the flip-flop to the input of the flip-flop. Since I came to the input of the flip-flop, I no longer have to deal with timing. So I remove the timing. I put the timing aside altogether. What that means is I am back to using Carnot maps, truth tables, and everything that I've learned so far. Okay? So my problem is now reduced to three variable Carnot maps. Okay? So let's now do the excitation tables. I'm gonna do the I'm gonna use this color. And the characteristic equation is the equation that tells you how to go from the transition table to excitation table. Okay? The good thing about the flip-flops, and that's why I'm using it over here, is that the transition table, the good thing about the flip-flop is exactly the expression I'm showing up there, which is transition table and excitation table. They look the same. I'm not saying they're the same table, they look the same. So the same zeros you put in there, you put in the other table, the same ones and so on. I'm going to implement my excitation tables. For implementing my excitation tables, I need 3 Carnot maps. The inputs Q2, Q1, Q0. This one is D2, this one is D1, this one is D0. Q2, Q1, Q0, Q2, Q1, Q0. I'm going to use a little bit darker color for the ones in the table. All right, tell me this. For Q2, Q1, Q0, 0, 0, 0, what do I need on my D1 or D2, D1, D0? 0, 1, 0. Okay? So let's just read from the table and fill in these Carnot maps. Okay, read the excitation table and fill in the Carnot maps. I'm done with this. How about 0, 0, 1? 0, 0, 1 is don't care. I'm done with this. How about 0, 1, 0? 0, 1, 0. What are you reading? 0, 1, 1. 0, 1, 1. Let's do the next one. 0, 1, 1. 0, 1, 1. This is spot over here is 1, 0, 0. 1, 0, 0. Okay? 1, 0, 0 is 1, 1, 1. 1, 0, 0, this spot over here is 1, 1, 1. So this is the one I was looking at. Okay? I'm reading Q2, Q1, Q0. And then what I put in my Carnot map is D2, D1, D0. For 101, 101 is this spot over here. 101 is this one, this one, this one, right? 101. Good. Don't care, don't care, don't care. 110, 110. Don't care, don't care, don't care. Finally, 111 gives you 0, 0, 0. Okay? I read my excitation table, put in my Carnot map, and now I have these Carnot maps here. Let's do the implementation of the Carnot maps. D2 equal I'm using still a darker color to distinguish this. This is Q2 bar Q1. ORed with Q2. It wasn't Q1, it was Q0. ORed with Q2 Q0 bar. Right? This one, D1, is easy. It's actually Q0 bar. How about D0? D0 D0. Is this with this, okay, which is Q2 Q1 bar ORed with Q2 Q1 bar ORed with Q1, which is this, Q0 bar. Okay, now let's do the implementation. What's D2, by the way? First of all, what I'm building is this. I get to Q2 in a second. What I'm building is this. I have 3 inputs coming in, Q2, Q1, Q0. Okay. And I'm providing inputs for the D flip-flops, meaning that I'm providing inputs for these 3 here. I need Q2 bar, Q1 bar, Q0 bar. What's D2? How about XOR of Q2 and Q0? Okay. XOR of Q2 and Q0. What's D1? Q0 bar, that's also easy. And what's Q0? Okay, I'm going to do the lines later. It is Q2 Q1 bar, Q2 Q1 bar, Q1 Q0 bar, ORed together, and that becomes the input for my Q0 flip-flop. And actually the excitation tables became this. Now the input of this table are Q2, Q1, Q0, and the outputs are D1, D2, D0 that with the next clock become Q2, Q1, Q0, and therefore what we do next is Q2 connects to Q2, Q1 connects to Q1, Q0 connects to Q0, and this is now my counter with these three outputs. Okay? So we are really back to where we were before, right? Before, we were dealing with Carnot maps, truth tables, trying to minimize and all of that. And last time when we did those counters, that was a special case. That was a case that we just happened to find the proper pattern so that we did all those AND gates and all of that. But if I'm not finding patterns, then I will do something like this. Okay? Something else I want to show you here, and that is really what I have is 0, 0, 0, this, 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 and this. Actually, I have 5 states. Okay? Each clock is taking me from one state to the next state. If I regard each one of these as states, I can call this diagram on top a state diagram. Okay? Before going to our next topic, remember we said that we are doing registers, shift registers, counters. I'm doing this counter, okay, or a general counter. And next I want to go to controllers, and actually they are the ones that use the controllers, the state diagrams. Let me very quickly let's do that. Let me very quickly go through a different counter, an up-down counter that uses instead of let's say D flip-flops, uses JK flip-flops. Okay. The counter I want to build this time is a small one, a 2-bit counter. Goes from 0, 0 to 0, 1, then goes to 1, 1, and then goes back to 0, 0, 0. If up is 1, this is the direction it goes. If up is 0, it goes the opposite direction. Okay, so that's the same state diagram, but see here I didn't have any control. Everything was in one direction. Now this state diagram looks a little bit more exciting, and that has actually each state has 2 directions. If up is 1, it goes in one direction. If up is 0, it goes in the opposite direction. So I'm taking this state diagram, which represents a counter, a 2-bit up-down counter, not the binary counter. I didn't say it's a binary counter, because if it's binary, it's counting from 0 to 1 to 3, which is not binary. Okay? I'm taking this 2-bit counter, whatever counter it is. It is an up-down counter. I want to build it. And what I have is a state diagram. The first thing I want to do, see, I don't like diagrams. I like diagrams when I'm describing something, but I don't like diagrams when I am building Carnot maps and truth tables, because they don't go with diagrams, they go with tables. They go with truth tables. They go with tabular zeros and ones. So the first thing I do after I have a state diagram is to turn my state diagram into a transition table. Okay, so this is my transition table. Let's call it Q1, Q0, 0, 0, 0, 1, 1, 0, 1, 1. Okay, or maybe I don't want to do that. I make it, let's do this, 0, 0, this. Okay, and then I have U equal to 0 or U equal to 1. If U is 0, Q0, Q1, Q0, 0, 0 becomes 1, 1. If it's 1, becomes 0, 1. 0, 1 becomes 1, 1. 1, 0, nothing. 1, 1 becomes 0, 0. This is the right direction. U1 is the right direction. U0 is the left direction. So 0, 0 becomes 1, 1. 1, 1 becomes 0, 1. 1, 0 doesn't exist. And 0, 1 becomes 0, 0. That's my transition table. Before I decided that I wanted to do a D flip-flop, and if I do D flip-flops, I'm all done now, right? Because all I can do is say, okay, Q1, Q0 is the same as D1, D0. So this table becomes my excitation table, and I already know how to do that. This time instead, what I want to do is I want to use JK flip-flops. JK flip-flops work like this. A JK flip-flop has its own excitation table. Okay, JK flip-flop says this. It says, if your Q is whatever value and Q plus is some other value, 0, 0, 0, 1, 1, 0, 1, 1. Let me use a different color here to because this is not something particular to this problem. It is something that you have to know. Q, Q plus, and then J, K. It says if you are going from 0 to 0, okay, you want to make sure that you don't jump it. Okay? But then, if your K is 0, it's fine. If your K is 1, it's also fine. Okay? Remember how JK flip-flop works. If K is 1, it kills it. If J is 1, it jumps it. Okay, so when I want to go from 0 to 0, if my present state is 0, my next state is also 0. Okay, I want to make sure that I don't jump it, but killing it doesn't matter. So either 0, 1 or 0, 0 will take me from 0 to 0. Going from 0 to 1, I want to make sure I do jump it. But then K doesn't really matter. Because if it's 1, 1, it's complementing it, which gives me 0 to 1 transition. If it is 1, 0, it's jumping it, which is going to give me a 0 to 1 transition anyway. 1, 0, you want to make sure that you do kill it. But then jump doesn't matter because 1, 1 means complementing, so it's complementing. 0, 1 also means that you are killing it. That means the output is 0 anyway. And then finally 1 1. 1 1, you want to make sure that you do not kill it. But then how about the jump input? The jump input doesn't matter. Okay? This is a table I use for my JK flip-flops instead of this. Actually, if I look at my D flip-flop excitation table, is as simple as this. 0 0 0 1 1 0 1 1 Q Q plus. What's D? Well, D has nothing to do with the existing Q. It is the same as Q plus 0 1 0 1, which is this expression over here. But and that's why my excitation table in case of the D flip-flop was so easy. In the JK flip-flop, things are not as easy. Okay? Now I have my Q1 plus Q0 plus. Let me turn this to J1, K1, J0, K0, and then I have U01, U01. Now let's look at this. My Q1 is going from 0 to 1. Okay? What do I want on J1? What do I want on K1? Okay? What do I want on J1? What do I want on K1? 0 to 1, J1, K1. Zero to 1, which is this. I want 1 dash. Okay. Q0 is going from 0 to 1. What do I want on J0, K0? 1 dash. 0 to 0, J1, K1, 0 dash. 1 to 0, look up there, is 1 dash. 1 to 0, sorry, dash 1. This is good. Okay. Let me show a few more of them before I do the complete. Let me do this. Let's take zero zero, changing to 0 1. Okay. Let's look at Q1 first. Q1 is changing from 0 to 0. 0 to 0 for Q1 means 0 dash for J1, K1. So what I'm going to do is in that column in here, for J1, K1, I'm going to put 0 dash. Okay. So 0 to 0 gives me 0 dash. But then here I'm doing 0 to 1 for my J0, K0. 0 1 means this. That 0 1 gives me what? 1 dash over here. Okay? So I'm going to do the table like that. So the next one, 0 to 1, 0, 1, 0, 1 is 1 dash, 1, 1 is dash 0. Then down here, 1 to 0, 1 to 0 dash 1, 1 to 1, 1 to 1, that's for K0, is dash 0. Then 1 to 0 is dash 1. And 1 to 0 for J0, K0, 1 to 0 is dash 1. I'll give you some good news at the end of this. While I have your attention, I'm not going to give you the good news yet. So what I have here is, instead of 3 Carnot maps, one for each of the flip-flops. Here I only have 2 flip-flops, and I have 4 Carnot maps for J0, K0, J1, K1. Okay? If I were to do this using D flip-flops, I only needed 2 simple truth tables. Alright, so I'm gonna do my truth tables here, my Carnot maps here. Well, a partially good news is that because of the JKs, even though I have more Carnot maps, but the Carnot maps have a lot of don't cares in them. Okay, so U Q1 Q0, U Q1 Q0, U Q1 Q0, U Q1 Q0, 0 1. This is J1, K1, J0, K0. Okay? And again, let me use a darker color to do that. And J1 is 1 0 dash dash, right? Okay, I'm taking this column. The next column of J1 is this one, which is 0 1 dash dash, 0 1 dash dash. Then it's K1, which is the column to its right, dash 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 1 dash 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 1. There are 2 kinds of dashes, right? One kind of dash is for the cases that never happen, like in this example, 1 0 doesn't happen. Another kind of dash, or don't care, is for cases that the JK flip-flop tells us that it doesn't really matter. Okay? Which is the property of the JK flip-flop. And let's do J0, J0. I'm taking this column. Okay, I'm taking this column for my J0, and I'm putting that into the so this column and this column, these become my J0s. Okay, so J0 are those 2 columns, and I'm putting them in my J0. So 1 dash dash dash. The next one, same thing, 1 dash dash dash. K0 dash 1 dash 0 dash 1 dash 0 dash 0 dash 1. Okay, and now my J1 is okay, nicely XNOR of U Q0 U Q0 bar. K1 is 1. J0 is 1. See, like I said, even though you have more tables, but you have a lot of don't cares. And see how simple these expressions are becoming. Okay, if you were doing D flip-flops, then true that you had fewer number of Carnot maps, but each of the Carnot maps would be more complex. You would have fewer don't cares. K0 is, the good thing is that I found the XORs. K0 is U Q1 U Q1, and that's XNOR of UQ1. Remember I said that XNOR you can either complement one of the inputs or the output, and since both of these are XNORs, I put the complement on my U input. Now let's do the circuit. Okay, the circuit has 2 flip-flops, Q1, Q0, a clock input, which I'm gonna do last, and then it has a D input here, a D input here. This is my D1, I'm sorry, not D, JK now. JK, C1, okay, J1 is U bar XOR Q0. K1 is 1, J0 is 1, and K0 is U bar Q1. Okay. This is my up down counter, counting the sequence I'm showing in the state diagram there. This is my clock, and this is my reset. Okay, the good news I'm telling you is in most designs you don't use JK. JK flip-flops, we use them like when I was a student. The only use they have these days is for exams, okay, and presentations like this, okay. It's important to understand them. It's important to know that something like this does exist, but a lot of people don't use JK flip-flops. All right. So what I've shown you is you can take a problem description, turn it into a state machine. Turn it into a state diagram, and turn that state diagram into a circuit like this. Okay? But then the state diagrams I showed you were mainly for counters. But now I'm going into what is called controllers. Okay, controllers are circuits very similar to counters. They have states. They go from one state to another state based on certain conditions, like this up down counter that I had. It goes from one state to the next state based on certain conditions. But a controller usually has many inputs, many outputs. That means a controller for a processor, it looks at the instructions, it looks at the overflow from the previous time, it looks at a lot of other things, and based on that it decides on certain control signals to be issued. So basically a controller is a very complex system with many inputs, many outputs, and then a clock and a reset, and makes a certain decisions. I'm not going to do a controller with 20 inputs and 20 outputs for you. Okay? I'm going to do a controller very similar to the counter that we did, with only one input and one output. The good thing is that with the controllers, whatever style of coding, style of description, style of design, procedure for the design applies to the little controller that I'm going to do for you, which is one input, one output. Everything applies to very complex controllers as well. Okay? So, forget about a controller with 20 inputs and 20 outputs. I'm going to do a circuit for you which represents in every aspect of design the same properties as a very complex controller. I'm calling this a sequence detector. Sequence detector has an input A. Let me use J. Input J, output W. I am defining this sequence detector as a sequence detector that in 3 consecutive clocks, if the input is 1, this is my clock, this is my J input. If on 3 consecutive clocks, when I say consecutive clocks, I mean on the rising edge of 3 consecutive clocks, if my input is 1 1 0 1 1 0, my output W becomes 1, stays 1, cleared through the next rising edge of the next clock. That's the circuit I want to design. And I'm guaranteeing that this little circuit represents very complex controllers. These circuits are called sequence detectors because they detect a certain sequence of ones and zeros on their inputs. And this is a finite state machine. To do this design, I start with a state diagram. Okay? I start with the state diagram. And then basically follow the procedure I have gone through here. So the key thing is, if I'm able to turn my circuit into a state diagram, if I'm able to turn this description, see, I already have the description for you, right? The sequence detector is detecting sequence 110 on its input. If I'm able to show you the detection of this if I'm able to show you a state diagram detecting this, then the rest of it would be very similar to this, very mechanical. Actually, much easier than this, because here I did JK flip-flop. I'm not going to do JK flip-flop throughout the course anymore. D flip-flops I'll do. So, the key thing right now is state diagram. After that, I do state tables. After that, I do transition tables. After that, I do excitation tables. After that, I do Carnot maps, and finally, I get the circuit. So let's start with the first step, and that is the state diagram. I start in a state called state A, and my output is 0. I am searching for sequence of 1, 1, 0 on the J input. If I receive any information that is worth remembering, I change my state. Okay, listen to this sentence again. If I reach an information that is worth remembering, I change my state. Well, this is the way we think, right? This is the way our minds work. Let's say you are going along a street, and then you are told that you're looking for an address. Okay? And you're told that there is a gas station, followed by another gas station, and followed by a convenient market. Okay? 7-Eleven or something. And once you see that, then the place you are looking for is right next to it. Okay? So you're looking for gas station, and then convenient market. As you are driving, you see the first convenient market, the second convenient market, the third one. Are you seeing any information that is worth remembering? Yes or no? You haven't seen any gas stations yet. You are seeing many, many convenient markets. So you don't change the state of your mind. So if I ask you, how many convenient markets have you seen? You don't have an answer because you haven't been counting. Because your state hasn't been changing. Okay? What it means is, for as long as I'm getting convenient markets, I stay in my A state. As soon as I see the first gas station, then this is an information that is worth remembering, and therefore I go to my state B. But still, this is not my address yet. My output is still 0. You have seen your first gas station. You're hoping to see a gas station right next to it. But what do you see? You see a convenient market. What happens? You say, well, the gas station that I was looking for is not this one, because there was supposed to be a gas station right next to it, which is not, and therefore you say, let's go back to the drawing board and let's start the search again. On the other hand, if I see another gas station, I say, okay, look, things are beginning to look good, so let's remember that I have seen another gas station. In this state, what if you see another gas station? You have seen two already, right? If you see the third one, what do you say? You didn't see a convenience store, but then you saw a gas station. So you say, well, I'm supposed to see two gas stations in a row, but I'm seeing three of them. So maybe the person gave me the address is giving the last two gas stations that I have seen. What it means is you have already seen two gas stations. If you see the third one, you say, well, I've already seen two gas stations. If you see the fourth one, you say, I've already seen two gas stations. What it means is that you don't change the state of your mind. Okay, because you have already seen two gas stations. So for as long as I see gas stations here, I stay in the same state. But then if I see a convenience store, I say that's set, I reach state D, and my output becomes 1. Okay, let's forget about gas stations and all of that. 110 I have received. I go to state D. What if I receive another 0? Well, another 0 is nothing that is worth remembering. I go back to 0. Okay? Usually when you are doing sequence detectors, you allow overlapping sequences. Overlapping sequences means that if you get another 1, okay, in this case I don't have any overlapping sequence. I'll give you an example. But if you get another 1, you say, well, fine, I got my output here, but this 1 may be the beginning of the next 110. All right? And therefore, what state do you go to? You go to state B. But see, when I talk about the overlapping sequence, and what if you're looking for 101, okay, and as soon as you get to this, your output becomes 1. But then if you get another 0, another 1, then you are reusing this 1 of the last sequence towards the next sequence. For now, don't worry about that. I will do examples that cover that. I'm going to the next page, and I'm going to do this state diagram again. The first step is to, instead of that diagram, turn it into a tabular form. So I make it A, B, C, D. This is my present state, and then this is my J, which is the input, either 0 or 1. This is state plus or the next state of my circuit. If J is 0, I mean A becomes A. If J is 1, I am in A becomes B. If I'm in B, J is 0, I go to A. If I'm in B, J is 1, I go to C. If I'm in C, J is 0, I go to D. If I'm in C, J is 1, C, J is 1, I go to C. If I'm in D, J is 0, I go to A. If I'm in D, J is 1, I go to B. All I did was just reading the table. Okay? And then I have my output here, which is 0, 0, 0, and 1 on the state D. So what I have done here is I started with my state diagram, and now I have a state table. Okay, I jumped ahead a little bit when I said the state assignment. State assignment doesn't come into play until now. All right. Now I look at this table and compare it with this table that I have over here. The good thing about this table, which enabled me to turn it into truth tables and Carnot map, is only I have zeros and ones. The problem with this table is I don't have zeros and ones. I have A's, B's, C's, and D's. Okay? So what I'm going to do is turn this table into something like this by replacing A, B, C, D with some bit patterns. I have 4 states. I need 2 bits to represent each one of them uniquely. Okay? So I make what is called my state assignment. Okay. State assignment means give a bit pattern to A, 1 to B, 1 to C, and 1 to D. As long as they are unique, you are okay. You like to give 1, 1 to A and 1, 0 to B, that's up to you. But then I like this pattern better because that corresponds much closer to my Carnot maps. And in the implementation, in the functionality of their circuit, it makes no difference whatsoever. So this is what I'm going to do now. Is 0, 0, 0, 1, 1, 0, 1, 1. I'm calling this one state variables V1, V0. And what I'm showing you here is V1 plus V0 plus. So the table, the red table on the left hand side has now become the tables with ones and zeros on the blue table on the right hand side, and then instead of all the A and B's and C's and D's, I put this assignment that I'm showing over here. So what do I put here? 0, 0. For B, 0, 1. For C, 1, 1. For A, 0, 0. For D, 1, 0. For C, 1, 1. For A, 0, 0. For B is 0, 1. And this is my transition table. Okay. The next thing I want to do is, what did I do here? The next thing I want to do is to remove these pluses here. The pluses mean timing. My Carnot maps don't have timing. To remove these pluses, I have to decide on the type of flip-flop. My last experience with using JK flip-flop was not a very good one. Okay, plus that all the flip-flops people use nowadays are D flip-flop, and therefore I decide that I want to use D flip-flops to go from my transition table to my excitation table. Okay, since I have decided that I want to do D flip-flops, this becomes, even though I'm repeating it, but you don't have to, this is my state table. This is my transition table. This is my excitation table. D1, D0. And somewhere your output is, we will decide on the output later on. It's really not the most important thing now. All right, what's next? After the excitation tables, which we are done, we do the Cardinal maps. By the way, notice that my excitation table and my transition tables, because I'm using D flip-flops, are exactly the same. Okay, and therefore I didn't really have to repeat it. I'm just repeating it because I wanted to show it to you for the very first example. I have, this is my circuit. J is the input, W is the output, clock and reset. We don't worry about that. This is 110 detector. And I have two Carnot maps for the D1 and D0. J is the input. V1, V0 are the state variables. Okay, and have already decided that I need two flip-flops. And I've already decided that my two flip-flops have a common clock, a common reset, and my flip-flops have one is called V1, one is called V0. These are pluses. This is C1, 1D, C1, 1D. These are my two inputs. Okay, and now I'm trying to find what happens to D1 and what happens to D0. D1 is 0, 0, 1, 0. 0, 1, 1, 0. D0 is 0, 0, 0, 0, 1, 1, 1, 1. Okay? D1 becomes V1, V0 ANDed together, ORed with J, V0, D0 simply becomes J. Okay, this is your circuit. You have a J input, you have V1, you have V0. For D1 you have an OR gate, you have an AND gate, you have an AND gate, V1, V0. And then JV0. Or together, and D0 is simply J. And then V1 plus becomes V1, V0 plus becomes V0. This is your J input. And those are your clock and reset. Okay, and this is the 110 sequence detector. Going back here, we did the Carnot map, and finally we did the circuit. Oh, something I forgot, which I said that it's not a well, you have to do that because your circuit doesn't have an output here. Okay, but then on the other hand, it's actually a very simple thing. So let's go back to this color, and your output is, there is another Carnot map for your output, and your output is in terms of V1, V0. Okay, and your output is 1 when you have V1, no, I'm sorry. Good thing that I noticed that this is 1110. Okay, you had it correct over here, but then your output is 1 when your V1, V0 is 10. Okay, what it means is V1, V0, 10. V1, V0, one zero. Just leave a big bubble. Okay, and this is the output of your circuit. Okay. All right. We are done with the state machines, and we still have a few things to do, and that is describing the registers and the shift registers and all of these in Verilog. And we have 2 more meetings next time, which we work more on state machines and a Verilog description of them. Okay, thanks.